Hi everyone, welcome to our video on one of the questions in the homework that we were given for which is due this week, and we are going to look at exercise 1.6 number 2A, which can be found on page 46 of our lecture notes. And it says determine whether or not there is a plane containing the given lines and an equation for the plane if it exists. And we are given two lines there, L1 and L2. And so we have got two questions that we need to answer. We need to say, yes, there's a plane containing, or no, there's no plane. And then if the answer is yes, then we can then determine what the plane is, or an equation of what the plane is. Obviously, an equation will not be unique if it exists. You can have several expressions of this for the same plane. Right. So for the solution, the way to think about it is, so I've put this as an aside. So this is not part of the solution, but this is how you can think about this question to be able to answer it. So we are given two theorems that speak about planes containing some given lines. And so we are going to try and apply them in our scenario right now to be able to answer the question. So the first one is theorem 1.6.7, and it says when L1 and L2 intersect at exactly one point, then we are going to have a plane, a unique plane, L1 and L2, which contains L1 and L2, right? And then the second scenario is 1.6.10 part 1, which says that if L1 and L2 are not equal and L1 and L2 are parallel, then we are going to also have a unique plane that contains both lines. Right, so let's look at these theorems and see which one we can look at. Maybe we are able to eliminate one of the cases just by observation. So the first scenario, L1 and L2 have to intersect at exactly one point. Well, we've got these lines, we don't really know, we can't really check. Most probably, if you use some software, you'll be able to see if they intersect or not. But let's just say by observation, we can't see that. And let's look at the second scenario. The second scenario tells us that L1 and L2 should not be equal. So that's scenario, again, just by looking, we can't see. Probably if you use GeoGebra, you'll be able to see. And then the second condition says, in this theorem, says L1 and L2 are parallel. Now, that one we can check because if we look at the direction vectors here, we can see that one is not a scalar multiple of the other. And because of that, it means that these lines cannot be parallel, right? And because of that, we can conclude that this scenario does not apply to our scenario, to our situation right now, because the lines cannot be parallel, or the lines are not parallel, to be more precise, right? So what we need to check is the condition in theorem 1.6.7, which is we need to check if L1 and L2 intersect, and if they do they intersect at exactly one point? And then we can then say something using theorem 1.6.7. So that's how you think about the question. So now we do the solution. So L1 can be written like that. We all know how to do that. And then L2 also like that. And then it's always wise to use different scalars, even though at this stage, it might not matter if you don't use the same scalar, right? If you use the same scalar here, it's still fine, but it's probably better to just use a different scalar at this stage, right? And then we say Y is a member of L1 intersection L2, if and only if y can be written as an element of L1, which would mean it would look like sorry about that. It would look like it would look like that, right? And this is for some t, right? And also for y to be in L2, it means it has to be something that looks like that. Well, a member of that for some s, right? It has to be something like that for some s. So we get that expression there, right? And since it's the same point that we are talking about, it means all these are equal, and so therefore we end up with minus t, 1 plus t, 3 plus 2t is going to be equal to 2 plus 2s minus 1 plus s minus 1 plus s. And from there, we know by definition of equality of algebraic vectors that the first component has to be equal to the second component. Sorry, the first component of the left-hand side has to be equal to the first component of the right-hand side, and so forth, right? So we end up with these three equations, and we've got two unknowns, and we want to check if we can find S and T that satisfy all the three equations. So here you can use whichever, whatever strategy you're comfortable with. Here, I observed that equation 2 and equation 3 have the same right-hand side. So I exploited that and then said, well, if that is the case, then that means 1 plus 3 should be equal to 3 plus 2t, right? It means that from 2 and 3, that becomes obvious. And then from there, I can find t, or we can find t by simplifying that, and then we see that t is equal to minus 2. And then from 3, I can then find my s. You can also use 2 to find s, and we see that s is equal to 0, right? And now we just want to check if this is true for all equations. So for 2 and 3, notice that I only use 2 and 3 to find what is s and t. So now, so it means that for 2 and 3, s and t are S and T all will satisfy those two equations, 2 and 3, because I only use 2 and 3 to find S and T. So checking out, it is sufficient to look at equation 1. So from 1, we can see that the left-hand side is going to be equal to 2, and then the right-hand side is also going to be equal to 2. And so therefore, that means that S and T satisfy all the three equations, right? So we've got exactly one point of intersection, which is the point 2 minus 1 minus 1. You can use S is equal to 0 here, and then you find what Y is going to be equal to, right? Or you can use T and put it in there and then see what happens, right? So you find out that the point is 2 minus 1 minus 1. And then from here, now because we found that there's exactly one point of intersection, it means that by theorem 1.6.7, there exists a unique plane P that contains L1 and L2, right? So we've answered the first part of the question. It exists. And that is coming from theorem 1.6.7. And then the last part, an equation for P, then what we just need to take is the direction vector for L1 and then the direction vector for L2, and any point on either L1 or L2 will work. So if you put any point that is in L1 or L2 here, and then the two direction vectors, then you get an equation for the plane P. well, it's not unique, so it is an equation. Notice that this is an equation, not the equation, but an equation. It's not unique because you can get several expressions of this of this plane in equation form. So for whatever point you pick, that will be a different expression. So here we just picked 0, 1, 3 as because we know this is in L1. You could pick this 2 minus 1 minus 1 as the first point there, and then you take the two direction vectors, and then you get an equation for the plane. And that is it. So that is the solution to this question. Thank you.